Alrighty, I hope you're able to acknowledge our little data pieces friends, or the emojis there screaming for help. Hopefully we'll be able to actually save them today by mitigating the divide between Kafka and Iceberg. A lot of the things I'm going to discuss today is going to be relevant for some parts of Delta Lake as well, because we are going to discuss elements of Parquet as a file format. And if you're using Delta Lake, you know that underneath the hood there is a Parquet format out there. Raise your hand. Has anyone heard about Apache Kafka? Everybody. Amazing. Keep your hands up if you're using Kafka in production. Everybody. OK. What about Iceberg? Iceberg in production. OK. Delta Lake in production? Awesome. OK. So a lot of people have both. That's really exciting. OK. So as you probably know, since you have Kafka and you have Iceberg and you have Delta Lake, many times we spend hours and hours as an engineer just to bridge that gap and help take data from our Kafka topics right into our analytics space that usually being populated by Iceberg format and Delta format. And these divide and some of the solutions that exist out there wasn't necessarily built for scale. And we're going to look into one of the solutions, and then we're going to dive deeper into how we can actually take it to the next level and scale it. So by the way, according to some industry benchmarks, usually 70% of the work that we do in the data space is exactly that, trying to mitigate in between two formats. It doesn't exactly behave the way we want them to behave, because they were inherently different. So hopefully by the end of this talk, you'll know a little bit more, and you'll be equipped to actually jump in and build that divide. So let's take the first step of us wanting to build it. Today in the industry, there are Kafka to Iceberg connectors. Anyone heard about Kafka to Iceberg connector? One, a couple of them. OK. Today there's a Kafka to Iceberg connector, which means it's more of a naive approach. Essentially, we can define a table of Kafka as a source as a first step. And then we can define an Iceberg sync table. And then we need some query engine, let's say Flink or Spark or what have you, to help us build that continuous, ever-streaming data pipeline. So now we have a Kafka table, we have an Iceberg table. Just bring it from one place to the other. Sounds easy, right? Pretty dumb pipe, right? Not a lot of work into it. So what? Most of the engineers will look at that and say, so what's the real problem here? Why should we care? And the real problem is when we're trying to scale anything like that, we're going to hit a lot of exceptions and a lot of loading problems, because essentially we're putting a bottleneck into the Kafka brokers, because now how these connectors work, essentially they're using our Kafka API in order to pull the information. That means they're acting yet as another consumer, and this kind of like, in the resource management, resource allocation, they're fighting for resources with other applications that try to read or write into these topics. On top of that, there's a couple of challenges on the Iceberg one, but we'll dive into it in a second. So a little bit about me. I wrote 2 books. One is the second edition of High Performance Spark, and one is Scaling Machine Learning with Spark. We're doing at 4 p.m. at the Riley booth. We're going to do some book signing. We're going to hand out books for free. I work for a company named Confluent, and Confluent, we're building a data streaming platform. Confluent started with Apache Kafka, so our CEO is actually the one that ideated and built Apache Kafka when it was just started in LinkedIn. I'm a people manager. I'm lucky to work with a lot of very smart people. I started my career in the machine learning AI side, moved into the data side when I realized that actually in order for me to do machine learning at a good, very well, I need to have a better data skills. And then it evolved from big data into streaming as it is today, which I also think it has an interesting supplementation to the agents world. But that's not the talk. This is the talk. So when we look at the Kafka connector that I just showed you before, it feels like, oh, this is going to be easy. And this is a Dunning-Kruger effect. Anyone heard about seeing this before? When we look at something, it's like, oh, it's going to be so easy. I can do it in my sleep. It's just going to work. And we just connect stuff. And then we realize that actually, there are things like schema evolution. Kafka topics doesn't really behave like Iceberg tables. And we'll dive into it. There are problems of consistency and partition. If you think you can take Kafka partition, Kafka broker partition, and just dump it into a lake, not really. And of course, there's the question of maintenance. At the end, when we are putting data into Iceberg, we want to be able for query engines to query it super fast. So if we have, let's say, customers, or if we have someone else on the analytics and the BI side, it's kind of like our internal customer in the organization, we want to be able to give them the data in a shape that actually is going to work well for them. So we need to make sure that we don't have small files, and we need to make sure we're compacting this data. So in Confluent, I work for Confluent. We build a solution, and this talk is going to be about how we build a solution and some of the internals of the things we had to build in order to enable it for our customers that asked for it. So we're processing more than multi-trillion events every hour, which is amazing. We have the biggest Kafka cluster in the world. Second after us is Uber. We have our solution takes your data, your topics from Kafka, and enables you to read them through Iceberg or through Delta Lake. And we are dealing with trillion multi-version schemas, which we're diving into today through the schema evolution. So Apache Kafka, many of you know it, many of you use it in production, but just a quick recap. So we have serialize, right? We have the Kafka producer, it serialized the data, it dumped it into the broker takes it in binary, and then when we want to read it through the Kafka consumer, we have to go through a process of deserialization. So let's jump into our first chapter of schema evolution. When I dive deep into my Kafka broker and how the data is saved there, essentially this data is saved into a key value format. This is a key value records of bytes, and it can be, I can work with different formats there. I can work with Avro, I can work with JSON, I can work with protobuf. If I compare it to an Iceberg solution or a Delta Lake solution, if you wish, it was more built for SQL data type. There is the notion of a table there. There's the notion of, rows essentially are stored mostly in Parquet. And we have a table with columns. So you can already see the differentiators between when I have a Kafka topic, I can put anything I want into it through the key value, versus in Iceberg, I have some restrictions around what can go where. So essentially what we want to do, we want to take the data from Kafka topics, we want to deserialize it, we want to apply some schema evolution, some work around it, and we want to update the Iceberg schema at the end to fit that evolution. Now, Kafka topics themselves can have multiple schema versions within one topic. So if I have a one Kafka topic, essentially I can have 10 different schemas, 10 different versions if I wish to, because if someone decided to write to this topic, there's not always a mechanism that helps me validate what is being written to this topic. It's extremely generic. Of course, we can add more solution on top of it, and we'll talk about it. But essentially, we have to understand that there is a huge divide. I cannot just take a Kafka topic and say, here are all the Kafka topics, all the people in the world, and now essentially this is now all the people in the world table. It's not going to map one-to-one. So how do we deserialize it in order for us to actually get the schema built in? We can rely on something called schema registry. So schema registry help us with a couple of compatibility modes. So when we're putting data into our brokers, it actually helps us enforce this different compatibility mode. So one of them is the backwards. This is essentially when consumers can read previous produced data. The second one is the forward. So consumers using old schema can read the newly produced data. And the last one is the full, which means I'm getting both the backward and the forward compatibility of all of them. And lastly, of course, there is what we call STRD, if you're familiar with that, but this is a serializer, deserializer implementation. This is something that we can provide and say, during that process, I want to add this guardrails on top of my schema so I can actually manage what is being written inside my topic. When I do that, I need to find a way to handle bad data. And my way to handle bad data is through DLQ, a dead letter queue. So I can make decisions, now that I have some rules around compatibility, I can make decisions and say, okay, now that I got this bad data, this null values, this out of schema property, what do I want to do? I want to dump it into a different queue so it won't end up in my data lake at the end of the day. Do I want to fill it out with some default value that I have? Or, I just want to dump this record completely and say, I don't want to process, put it somewhere else, and then just delete it. This is another option that I have as my data being materialized. And so this was the Kafka side. How does schema management happens in Iceberg specifically? So this is a really interesting one, because it's very different than how Kafka and schema registry manage that. At the bottom, this is the manifest. This is how Iceberg manages all of its metadata. You can see at the bottom, we have the data layer. So at the bottom, it's actually my Parquet or my Avro files sitting down there. A little bit above, there's the manifest file. So the manifest file could have different schemas that they're already pointing out to. On top of that, there is a snapshot. So snapshot is actually where I can manage some of the version. I can have a snapshot of the specific data at a specific time, and then I can have another snapshot of a different time where I have a different schema. At the top, and this is an interesting one for Iceberg, at the top, my table only has one schema always. So there's no way for me to manage it directly through the table. Every time I have multiple schemas, I'm going to manage it through the schemas underneath, through the snapshot. And essentially in Iceberg, the tables is always one schema. And this is where a lot of the engineers I got to interview and work with also failed on this step. So this is something critical for you to understand, that the table is always the latest schema that Iceberg has exposure to. So how do we decide which schema to use in this serialization, right? How do we move from the Kafka topics into my Iceberg? How do we handle incompatible changes? How do we do it seamlessly? And most importantly, how do we automatically do that? Because usually all of you have Kafka in production. You know it's not just one topic. You usually have multi-thousands of topics at some point, depending on the size of the company and the size of the solution that you're building. So what can we do? What are options? One option is stop the world. Oftentimes, we don't want to do that. Our engineering managers don't want to do that. Our product teams, our sales team, no one wants to stop the world. We want to continue operating. The second option is ignore bad changes. Now there was a schema, something happened. I can ignore it completely and dump the data. This is data lost. In some scenarios, it's going to be OK, but for some scenarios, not. For example, if I'm working for a financial institution, data lost of financial transaction is a big no-no. I don't want that to happen. The next one is write-to-deal queue, like we spoke about before, dead letter queue. It's a known architecture pattern. We'll fix it later. This is one option. And the last option is adapt the schema to handle the changes. This is what usually a more mature solution will do, and this is what we're going to dive into. What are the different strategies that we can adapt the schema to handle those changes? One of them is we can decide every time we have a new schema, we're going to go through our Kafka and schema registry that works together in order to manage the schema and just convert to the latest schema and schema registry. Every time I want to bridge that divide, it's going to be a dump decision that my system is going to do. Go to schema registry, tell me what is the latest schema that you have in there. This is going to be the schema for my Iceberg table. The second option that we can do is to create an Uber schema. Uber schema means that I'm capturing, it's a huge schema at the end of the day. It's because I'm capturing all the different permutations of the data and all the different changes. Here in Uber schema, I don't delete. So for example, if I have in my Kafka topics V1, V2, V3, V4 of the same data, I'm not going to delete any one of these potential columns. Each one of these columns are going to have a dedicated column in my Uber schema. Yes, even if I have like the same address, but one address came in as a string and the other address came in as a byte, I'm still going to represent them in my Uber schema. Here specifically addressed byte array and the address as it was originally. So this is another solution of how we can make sure we're not avoiding any data loss. I want to mention another thing here that related to data. Specifically in Avro, there's something called type widening. Anyone heard about type widening in Avro? So type widening is built in Avro, and the goal here is not to lose data. And the idea is that int can become a long, because there's no, we're not losing that data in that transition. Another challenge that exists here, and the reason for the Uber schema, is some of the type widening rules, specifically in Avro, doesn't really correspond to type widening rules in Parquet or in some Iceberg format that are not Avro. Even if Avro, there are some limitations there that are enforced by Iceberg. So something to think about it, that some of these type, for example, if I have, my address is a string, my address as a byte array, well, Avro still able to handle that internally, even when I enforce schema because of the type widening. Iceberg won't be able to handle that with Parquet. Let's talk about the second challenge. So the second challenge is consistency. Consistency of the data is always a big challenge for us because we want to make sure that every time we have any data in our Kafka topics, we want to make sure they're finally materializing well inside my Iceberg table as well. So how does the solution that we build help? So let's assume I have a Kafka cluster. You can see I have some topics. I have some data that I read that was already materialized, and I have some data that wasn't materialized yet. So what we decided eventually is because Kafka partitions doesn't map, because all the reasons I outlined before, it doesn't map one-to-one. What we decided to do is we decided to build a dedicated service around Tableflow. So what my Tableflow is going to do is going to call a Kafka cluster, and it's going to fetch the topic, the partition, the start at the end. And the reason that it's going to fetch it from it, because I want to manage these offsets, I want to manage these reads outside of my Kafka cluster. I don't want to create any more burden on top of my Kafka brokers. I want to take that information away and have a different service managing it for me. Now, the way we build our Kafka cluster, Kafka specifically can have its own storage and compute in one machine, but you can also have different tiers of storage if you wish to build that. And so we always have object storage, data information, and object storage as well, because we need redundancy, because the data, we don't need the data in one single digit latency all the time. So what we're leveraging here when we're building the Tableflow solution is we're able to actually go and fetch these segments from the object storage. So my Kafka cluster now would go fetch the segment and return this segment to Tableflow. So once it returned which segments to read, not the data itself, but pointer to the data, right? URIs. Once it fetches back, Tableflow can later manage that operation against object storage. So this is how I'm removing that dependency from my Kafka cluster. I'm enabling my Kafka to continue doing its work, serving its customer and the organization, and I'm loading that, moving data from Kafka to my Iceberg to a Tableflow service. So now Tableflow is going to fetch that segment from object storage. Now this is extremely different than what we had with the connectors that we saw in the beginning. I know many of you weren't really familiar with the solution of the connector, but the solution of the connector actually missed that part, because the solution of the connector puts all the loads into my Kafka cluster. So now we're reading all the topics, we want to dump them all, but it all goes through workload, it becomes a workload on my Kafka cluster and not this more sleek solution. So what do we know on the consistency on Kafka side? We know exactly which partition and which offset for each one of them, because we're fetching them from Kafka and we're managing it. Topics partition in Kafka, when they materialize on disk or on object storage in the cloud, they're called segments. In case you didn't know that, but something to know. And it gives me better possible parallelization. So now for every segment, I can have a dedicated thread that goes and fetch that. So I'm not dependent on my Kafka at all. Now, how does consistency works when I want to write to Iceberg? Has anyone ever looked at that diagram around consistency with Iceberg or consistency with Delta Lake? Yes, some folks. OK. So Delta Lake and Iceberg actually works pretty similar on that front. Usually, they use something called optimistic concurrency control. That means that they don't want to lock access to the data completely, but they have some estimation, and they're optimistic that something is, the process works well. But they do have one very strong lock, and this is called, when we do the scan, write data, refresh metadata, and conflict check. Conflict check, this is where I'm getting my lock. So that means no more distributed accessing. I only have one thread that can access it every time when I'm going through the conflict check. This is how Iceberg guarantee this consistency of the data later on. So only one writer can pass that conflict check at a time. This is how Iceberg promised this consistency. This is the Iceberg commit path. If you're curious to learn more, there's some URL. I think it's covered by the gray part there. But I'll share the slide over LinkedIn. You'll have access to it, and you can read deeper if it's something that is interesting to you. So how did we go about consistency when we build Tableflow? So we talked about bringing in the segments, right? And for every segment, I want to make sure I'm managing that consistency while interacting directly with my Iceberg table. So I'm adding two more services. One is a materializer of the segments of the data itself, and another one is the committer, because I want to create something like a two-phase commit that's going to make sure I have all my data right in there, as consistent as possible. So after bringing the segment through the materializer, writing into the object storage for Iceberg table, wherever my Iceberg table lives, I'm later on sending that commit to the committer. And the committer later on is going to process the schema evolution, what needs to happen, if there's a new schema or not, and it's going to work against my Iceberg catalog. Here specifically, I put Unity catalog because you can use it with Unity, but you don't have to. You can use it with Glue, you can use it with Polaris, whatever catalog that you wish, because we built Tableflow in a way that is generic. It gives you all the metadata that you need, and then later on you can pick it up and read it and connect to whatever catalog you wish to connect. So here we have committing the task, and then we're writing the Iceberg metadata according to the segment that we just did, and then we're finalizing with the latest commit offset of where we committed the data. And this is how we guarantee that consistency in between these two very different frameworks. Now, the last part. Has anyone suffered from small files? Everyone. OK, so we all know it's kind of annoying, because we want to build a query. And if you work at the data infra world, many times you'll have internal customers, and you'll be like, hey, this query is really, what can you do about it? Well, you kind of did select start. There's nothing for me to do about it if you do select start. But when a small file usually doesn't talk about, we can suffer from that with select start, but usually small files means I have to do more I/O ops, which means I have to go to I/O to the disk more times. And that travel of this query to get more information, essentially what makes it extremely slow. So once we're fixing small files, what we call the table maintenance stage, we actually enable our analytics folks to be able to read everything much faster. And so some of the service that we built, we actually wanted to make sure that whoever used that will also benefit from not needing to deal with small files, because small files can be pricey and they can be annoying. I don't know if you read this article from an AWS guy, but essentially they were fixing small file and compaction for their internal BI solution, and they were using Spark initially because you can do compaction with Spark if you wish to, but they wrote a very long article about why they moved from Apache Spark to Ray specifically, because Ray enables them to do that compaction much cheaper. So they saved something close to $100 million. That is engineering, that's a lot of money. Only on that compaction one. It's because Spark wasn't built for compaction. Spark was built for querying specific file that doesn't require doing a full scan of the data, which compaction does. Let's dive into small files. So small files mean that if I have my metadata or a catalog, I'll have increased metadata overhead, because that means for every file, I need to track it. I need to know where it is. I need to know which schema it's part of, which version, and so on. I have IOPS, like we talked about before, slow query performance, like we talked about before. And let's dive a little bit deep into why it is. Here I added the Unity catalog, but again, it could be a different catalog that you're using. But essentially what you can see there, the different level of what usually a catalog will have. There's a metadata level storage that manages the storage location, which means it holds pointers to where my data is, which means we'll need to hold pointers to all these files. I have the catalog level storage, again, where the schemas and so on, and the schema level storage. And if you look at a Parquet file structure, if you didn't get a chance to look into it, you can see at the bottom there is version, schema, footer length, and metadata, and a bunch of other stuff there. But the footer length essentially has to meet the block of the file that I have there. When I'm saving the data in object stores, there's a limit of block. I can't have a tiny, tiny block, which means I'll need to read the data even if there's no data there. So even if I had just a footer length information there, I still need to bring all of that object into memory in order to parse it and work against it. So this is one of the big reasons why we are suffering from these small files syndrome. And this is just the top of that. There's always a magic number. Don't change it. There's a row group, columns, and information about the file. And so essentially every catalog will have a pointer to all of these Parquet files wherever they are so they can manage and bring them right in time. So what are some of the strategies that we have for compaction? One of them that is highly used in Delta and Iceberg world, the bin packing heuristic, essentially trying to combine files efficiently as much as possible and honoring some constraints like size, schema, partition, boundaries, and so on. So we'll try to have, respect that boundaries, but still bin packing them as much as possible. Second one is trigger condition. Based on the number of files, I reached 10,000, 10 million files. Let's compact them. I reached a specific size threshold of actual information that is not part of the footer. Let's squish them together. I reached a threshold in time. Let's say I want to have that every 1 minute, 5 minutes, an hour, 2 hours a day. I can have that as a trigger. The next one is the size-aware policy. Some people are using that strictly. Another one is the metadata table compaction. Again, we have to make sure we are compacting the metadata too. We don't want that to explode. Usually it will have a strong consistency database behind it that helps us actually save all that data and that consistency. And another one is a partition-aware compaction, because we want to, as much as possible, try to not move data from place to place too much. So this is a very important one. There's also commit policies for Iceberg. I don't know if people here use that, but there's some interesting work around commit policies with Iceberg that essentially helps us balance some latency according to file size, so we can define them. The strategies that we decided to go with is trigger condition, because at Confluent, we're building a data streaming platform. We care a lot about getting data to people right in time when they need it. We care a lot about low latency. And so we build that so anyone who wants to use it can actually decide if they want it every couple of minutes or what's the size thresholds that they want to work against or the number of files. But we tested all of them, and that was the only one that actually fit what we needed specifically. Let's look at overall necessary optimization that we need to do with Iceberg on the maintenance side. So we need to prune all snapshots, right? Sometimes there'll be dangling files just hanging out there, so we need to make sure we are deleting them. We need to make sure we're garbage collecting, all unreferenced files out there. We need to make sure we're compacting the metadata files together with the files themselves. So compacting the data files and so on. A little bit about how we build it at Confluent. So essentially what we have is we have a nice UI that we built for using Kafka. You can see on the left side, there's one of the clusters, one of the experimental clusters, and you can see there are different topics and topic name, airline, and so on. And then every engineer that actually needs to take that data and materialize it into either in Iceberg format or a Delta Lake format can click that enable Tableflow and have that right in there for them to hand it off to the analytics team. So we wanted to abstract it completely from anyone who is using our Kafka solution. And there was a lot of requests around Delta too. So the journey started with Iceberg, and a lot of people are using Iceberg. And recently we started adding Delta as well together with Unity Catalog, just if people are curious to learn more about that. A little bit about resources, if anyone wants to dive deeper into our solution, how we build it, hear more, get into the weeds of that. The first link is really honing into how connectors work and what's the difference in them. There's a lot of different aspects like type widening and so on that I got into some of them, but there's more to learn about how to do it. The second one dives into table maintenance. So you see the red link actually dives into table maintenance. What are the things that we need to know and do in order to hand that table into anyone who wants to use it. The third one is actually Kafka KIP. KIP, for everyone who doesn't know, is a Kafka improvement plan, proposal. Essentially, it's part of the open source solution. Everyone in the world can open a Jira ticket and suggest a performance improvement solution. In order for Kafka itself supports consistency and the different guarantees of exactly once at most one or at least once. But the challenge is when we need to bridge different frameworks together, we actually need to find different solutions to create that consistency and that two-phase commit across the different solution. So this is the ticket, and the ticket is solved. You can look into it. That's KIP 939. It's open source. How to support participation in two-phase commit, that Kafka is leading, but we want to make sure we are actually following it and bridging that into other solutions. So you can think about things like Spark, if you're working with Spark, or if you need to bridge into Iceberg. Yes, and last one, there's a YouTube video about small files that dives into how really object stores works. What is going on behind the scene? Why are these small files so annoying? And dives into like the nitty-gritty parts of that. All right, yeah, that's it. Thank you so much.